Transistors are referred to as bipolar junction transistors. We have two categories, right? We have BJTs and then we have FETs, which is field effect transistors. So we'll look at bipolar switches. We have two types, right? Everybody okay? Okay with the two symbols? Yes, no? What's that? 9 in the new book. I don't know. Chapter. It's the first transistor. There's DC switch. I think that's the title. I think it did. I don't have the same book y'all have, but it's close. So you got two chapters. You got chapter 9 and you got chapter 10, right? And one of them should give you the basic symbols. The not pointing in, which is the NPN, and then pointing in, which is PNP. Are you okay? And we use a term called bias. What's bias? Huh? No. Bias is a DC voltage. It's a DC voltage applied to semiconductor devices. To establish or set their operating characteristics. Parameters. So to cause an NPN transistor to work, we have to make the base positive in respect to the emitter, and then we have to make the collector positive and more positive in respect to the base. To make an EPN, this is an NPN. To make a PNP work, we have to make the base negative in respect to the emitter, and we have to make the collector more negative than the base. And we're going to use these, and we'll look at some of the things that we can do, and it explains a lot when we get into the classes of amplifiers and the advantage of having both. But basically, PNP normally works on negative supplies, and NPNs normally works on positive supplies, even though we can make the NPN transistor work on a positive supply. And we have 3 regions we can operate these things in. What's their 3 regions? Cutoff to saturation. So when we cut off, we act like an open switch. When we're saturated, we act like a closed switch. And normally, we don't work the transistor saturated all the time, because if I operated saturated all the time, then I would use a straight piece of wire, right? You understand? Normally, we don't operate it cut off all the time, because if I had it cut off all the time, then I wouldn't connect anything up. So normally what we do, if we use this, we switch it between the two. And the third region is what we call the active region. In the active region, it acts like a rheostat, right? And this is where your stereo amplifiers operate at. you know, anything that does volume or and stuff like that. I'm constantly, if I wanted to amplify something, then I use my voice to move the transistor in its active region. So we have DVDs which are digital, but by the time it hits your speakers, by George, it's got to be what? Got to be analog. We don't send digital to speakers. So somehow we got to get that between the two, and we'll talk. We might get into a little bit of that. I don't know. And what we do is we're using what's the 3 leads? Yeah. And what we do is we use a base current normally to control the collector current. And we get a gain between your collector current and your base current. That gain is what we refer to as beta. And we use the Greek symbol for beta. And beta is calculated by IC over IB. Most data sheets don't use beta anymore. They use H of FE, and we'll look at this in a minute, which is still equal to IC over IB. So if you're looking at data sheets, you're looking at the forward current gain, but it's going to have a designator of H of FE. We don't see beta used except in books now. And why? I don't know. Reverse bias, everybody okay there? This is what you're going to do. The first time you're going to do, by the way, and we should have talked about this a little bit when you get the transistors, is we're going to bias it with 2 power supplies. And of course, we're going to use variable power supplies. And what you're going to do is you're going to set a voltage. And you can see where this guy here is connected between the watt. Yeah, this is connected between the watt. What's this lead right here? And what's this lead right here? And right here, this is the base. All right. Yeah. Now this battery is connected between the watt. Okay. And then we got a base resistor right here. We got to have a base resistor because I can't put voltage directly on the base. And why is that? Huh? Could, because it's a P-N junction, right? You understand. And as soon as a P-N junction turns on, it's a short circuit. It's a closed switch, right? So as soon as we come up here and get this, get above approximately 7/10 for a silicon transistor, then that switch closes right here and we start having current flow. Well, if I don't have anything in there to limit the current flow, then we could burn the base emitter junction up in no time at all, right? You understand? So we got to have that resistor. So we come up here, and we even had this in our power supplies. We always put a load out there, right? So the current flow through the diodes had to go through a load resistor. And then, of course, what would happen is I would come up here, and let's say I get this, I put 3 volts right there. Now, what's going to be dropped across this resistor right here? If it's a silicon transistor. It's not, 0.7 is being dropped across the base emitter, and Kirchhoff's voltage law says the sums of the voltages in a loop have to be dropped. So the resistor's not dropping 0.7, the transistor is dropping 0.7. What's the resistor dropping? 2.3 volts. Are you okay there? Approximately. We understand that it's not exact, but it's close enough for us to calculate, right? Y'all understand that? And then I could come over here and what would IB be equal to? Well, the base current, this is a series path right here. So the base current would be equal to 2.3 divided by the size of that resistor, right? You understand that? Everybody okay? Now what that's going to do is it's going to generate a current flow through this guy right here. And you can notice we have two currents going through the emitter. What's our two currents going through the emitter? Base current and collector current. So this is why IE is equal to IB plus IC. So when we talk about the biggest current flow in the transistor is going to be your emitter current, followed by your collector current, followed by your base current. Your base current is going to be the lowest current available. Now over here, we're going to generically refer to this resistor right here as RC. How much voltage is RC going to drop?
Power source to the emitter, they draw, you know what I'm saying, like making them decisions. So then we get back to the source voltage after we don't pay it.
Well, what you got is you got Kirchhoff's voltage law, and this is what we have now. We got this, and if we don't saturate or cut off the transistor, we've got this. And then I come over here, and then I've got this power supply over here, and then this comes around. Now this is the collector circuit, right? You understand? This is the base circuit. So we got a power supply, then we got a base resistor, and then we have a diode, and this is our circuit for the base. Now what's so interesting is that this circuit is controlling that rheostat right there. It's pretty interesting, right? So as base current goes up, then my collector current goes up. Now of course if the collector current goes up, the emitter current's going up too, right? You understand that. But how much voltage we drop across the transistor would depend on two things. It would be equal to the R of the transistor and then the R RC, right? Now what's the problem with the R of the transistor? It varies with base current. But what happens is that, so what I would have to do is I would have to have a way of being able to calculate the current flow through this side over there. Well, the way I calculate that thing is I use the ratio between the collector current, it's called beta, is equal to what? So what would that mean IC would be equal to? Yeah, it's going to be equal to IB times beta. Y'all understand? Now this is an approximation, and we're going to look at this in a minute. The problem we have with beta is beta varies. For one thing, if we don't have the ability to make two things exactly the same. So that means I look at a transistor and it's got a number on it, then it means that beta is going to be within a range, right? You understand? To get that number on it. Another thing is beta varies with temperature, and we'll look at this. We'll hook a heat gun up to this thing and watch the transistor saturate, because we don't have any temperature control. So normally when we design circuits, we try to do something that prevents the thing going the thermal runaway, and we'll look at that as we go along. But what happens over here depends on what I'm trying to let you know is what happens over on the collector side, and the collector emitter side is controlled by what's happening on the base side, right? You understand? So what we're doing is we're using base current to control the opening and closing of the valve. And it works just like a water valve. So water valves, we can cut them off, right? You understand? Or we can do what? We can turn them wide open. Or we can do what? Or we can operate it between cut off and all the way on, and we call that the active region. And you get an advantage over using a transistor, right? So what we're doing is we're taking very little base current to control a lot of collector current. So a transistor is nothing but a current valve controlled by a lead. On a bipolar transistor, we control it by a lead. We control the size of the valve by a lead called the base. At FETs, we control the size of the valve with a lead we call a gate. I mean, but they work exactly the same thing. Transistors are current valve. Transistors, right? So it almost says resistors, but we can transit or control it with one lead, and we're going to control the current flow between two leads. Base region is lightly doped. We've already went through this. Collector region, it pulls it through that reverse bias junction, right? And we looked at this. We looked at the two symbols. Kirchhoff's current law says that we looked at this. We went to the relationship between our currents. When we get into calculations, we're going to assume that IE and IC are approximately equal to each other, because they are. I mean, 99% of the current flow into the emitter goes out the collector. Saturation, everybody okay here? Yes, no? The three regions, excuse me. Okay. And this is where we left off. When a transistor is operating in the active region, the collector current is proportional to the base current. The DC beta is the current gain of the transistor and the ratio of the DC collector current to the DC base current. Beta has no units. It is not amps, it is not ohms, it is not volts, it is not Tuesday, it is not Wednesday. It has no units. It's a multiplier, right? And the analogy we use is when they give you a raise, you know, sometimes they tell you the dollar amount, but most times they give you a percentage. And the percentage is not a dollar value, it's something I multiply times my current wage to figure out what kind of raise I'm going to get, right? DC is a constant ratio called the current gain, is usually designated as the H of FE in the data sheets. And this is what we call the hybrid parameters. It's the forward transfer ratio with the emitter pointing toward the common. That's what that means right there. So notice on every one of these, the emitter is pointing, on these two right here, the emitter is pointing toward the common. And we can look at the data sheets. I should have told y'all to go ahead and log into Blackboard. Some of y'all might already be there. And we're going to be dealing with a transistor called 2N3904. And a 2N3906. We call the 3906 is the complement to a 3904. A complement is just the opposite of. So the 3904 is an NPN, the 3906 is a PNP, and they have exactly the same parameters. Except over here in the 3904 where everything is positive, over in the 3906 they would be what? Negative. So we call them complementary pairs, and we'll look at later on when we set up some of our stereo or amplifiers for stereo what we need complementary pairs for. I don't know if I've got these on the student drive or not. Solid state. What's that? Data sheets. And 2N3904. 2N3904. And it comes in a TO92 pack. And what does TO stand for? I told y'all, I just don't remember. Transistor outline. Just as a JEDEC registered pack. So there's a lot of things that use the TO92 package. So don't, just because you see a TO92 package doesn't mean it is a transistor. So this is the TO92 pack right here. So what have I got here? This is the Heath number, so we'd have to look this up. This TO92 pack. So it's flat on one side, curved or circular on the back side, and then we have 3 leads coming out the bottom. And we'll look at this later on. I can show you how you can identify the leads. There is no set standard on what is assigned to the leads. All the TO92 does is supply this case, this length, the space in between those leads, right? You understand. This could be an integrated circuit. It could be a voltage regulator. A fixed voltage regulator requires 3 leads. It requires an unregulated in, a regulated out, and a common, right? You understand that? Could be a triac, could be an SCR, could be, like I said, an integrated circuit, or it could be an FET, or it could be a bipolar junction transistor. Here you go, Corey. And so just don't assume that they're all the same. You know, even if I see this guy right here, this is a TO3 case, and this could be just about anything too, that requires 3 leads. The trainer uses a TO3 case for the 5-volt regulator, and the one they're using seems to be a piece of crap. We done topped on to how many of those things. My camera's fine, it's just it won't let me turn it off. Oh, there it was. There we go. Yeah, I don't see my integrity thing down here. I know it's still recording, but so this is the formula. This is what I wanted to show you. Though. Okay. So when we look at the data sheets, we start off with these breakover voltages. Voltage collector to emitter with the base open, voltage collector to the base with the emitter open, voltage emitter to base with the collector open. And this shows us our breakover voltages when you try to exceed a voltage that's required on the then we have IC, the IC saturated current, which is 200 milliamps. So 200 milliamps if you saturate the transistor. If you operate in an active region, then you're depending on something else. Then we get down into our electrical characteristics, and what we're doing is we're looking for the beta. HFE, DC current gain. And you can see the beta of the transistor could literally be anywhere between 30 and 300. So we have to take the beta with a grain of salt, and we'll see where we can use this. Now, once the beta of a circuit has been established, then normally we're okay. It'll always fall somewhere between this range. But when we deal with a switch, then saturated switch, which we're going to look at later in a minute, one of the main uses of a transistor is as a switch. This is one of the reasons that they took off so fast, was that we could replace these mechanical switches with something that was electronically controlled, right? And now all of a sudden I can turn things on and turn things off with very little current, right? I can come over here and hit a little button on my cell phone and turn on my cell phone, right? With a saturated switch, right? You understand that? You know, I can do all types of neat stuff. I can control a microwave oven with these little old touch buttons on the front. And I can control a lot of power, right? Turning things on and turning things off. But instead of doing it with a switch, we can do it what? We can do it electronically. And we can do it extremely fast. We've had relays around for years. These are electromechanical switches. But the problem with relays is they take a lot, they're slow. And these bipolar transistor switches are extremely, extremely fast. So we'll look at this in a minute, but this is part of the spec I wanted you to look at. And we say when we saturate it, we say it acts like a closed switch, but it can't be a closed switch because it is not a switch, right? You understand? This guy right here says it's going to drop a maximum of 300 millivolts when we saturate it. So for all practical purposes, 300 millivolts is hardly nothing at all, right? But you'll never measure 0 volts across a transistor when it's operating. If you measure 0 volts and you've got a problem, then odds are the transistor's shorted collector to emitter. Or something between the collector and emitters is shorted. If you got a switch, you're going to measure 0 volts across that thing when it's closed, right? You understand that. But a transistor, you'll never measure 0 volts between the collector and emitter when it's turned on. You'll measure less than 1 volt when it's saturated, and then you'll measure your collector voltage when you're cut off across the transistor, and then if your active region, it's going to be somewhere between those two. Hopefully right in the center. And we'll get in here and we'll look at some of these, but here's your breakover voltages right here. Y'all understand those breakover voltages? It's not an open switch. There's a path through there. If we break over a transistor when it's supposed to be cut off, if we push current between the collector and the emitter, then the transistor is going to be damaged, right? And if we exceed the reverse bias voltage on the base to emitter 6 volts. So that means if I let more than 6 volts reverse bias get on my base to emitter, then it's going to break over and you're going to mess the transistor up. The problem with transistors is they can open, they could become leaky, they could short, they could do all types of things. Transistors do all types of things when they go bad. And how do we check them normally? With an ohmmeter. So here's our 3 formulas. So DC beta is equal to IC over IB. So IC would equal to approximately DC beta times IB, and then IB would be equal to IC over beta. Operating at the same temperature. If the temperature changes, if the temperature goes up, what would you expect beta to do? Beta goes up. No, beta goes up. Yeah, so if you heat it up, then we get more current flow between the emitter and collector, and with the same base current, right? You understand? So beta varies in the same direction as temperature. This should be on the formula sheet that you got somewhere. The problem with these is that beta is not a fixed value, right? Beta is going to vary between transistors at the same between the same type of transistor at the same temperature, and then it's going to vary with temperature. We have a HFC, which shows us the relationship between the collector current and the emitter current. And we refer to this as DC alpha. And we use the Greek symbol for alpha. And it's going to be equal to IC over IE. When I look at the data sheet, we'll notice there is no listing for DC alpha. The only listing we have is for DC beta. Right here. HFE. I don't see an HFC. And why they don't do that? Because it's easily calculated from beta. Oops. So alpha is equal to beta divided by beta plus 1. Because what we're doing is we're finding the relationship between the collector current and the emitter current, right? IE over IC. Now what the problem is IE is always greater than IC. So DC alpha will always be less than 1. So this is the way we calculate alpha. We have 2 ways we hook up a transistor, by the way. We got 3 leads. And we can make one of the leads common to the input signal. So we have what we call a common emitter. What would the other one be? Common collector, common base. Common base is very, very seldom used. So the 2 main arrangements we have is what we call a common emitter and a common collector. And both of them have really, really good features. There's probably a 99.99% chance that when you drive a speaker, it's going to be a common collector driving that speaker. When we deal with common collectors, we are going to deal with the alpha of the transistor. Common emitters are used to get a bunch of voltage gains. Common collectors are for current gains. Common emitters is for voltage gains. So we usually use common emitters to take the input from that little old tiny DVD disc coming in, and we'll get a bunch of voltage gain out of it. And then when it comes time to drive the speakers, we're through with voltage gain, right? You understand? And what we're looking for now to drive a speaker? Current. Yeah, well, that's what makes a speaker work is current. You know, it creates a magnetic field. So if you're in stereos and stuff like that, you're going to run into both arrangements. Common emitter is going to gives you real good what? Voltage gains, and then common collector gives you real big current gains. Common base we almost never use, so even though I don't even think the book covers common base in here. The only advantage common base has is that it responds extremely high to extremely high frequencies. It's a very low input impedance. So this is a dual voltage, and we'll start off with a dual voltage bias. And then we'll move into single voltage bias. Just about all your amplifiers now use single voltage bias. And what we have to do is we have to learn how we designate these voltages within the circuit. Number one, normally when we measure voltages in an electronic circuit, we do not use two leads in the circuit. We measure everything relative to circuit common. And why is that? It's a lot safer, right? We can take our black lead when I'm troubleshooting in my car. I can clip it onto a good ground somewhere, and now I'm moving inside my circuit, and I don't have to worry about shorting out my car battery out there that's got tons of amps available and melts my little meter lead in my face, right? Blows fuses and all kind of stuff. It can still happen. Of course, when you pull your battery out, which lead you're supposed to take off first? The black. And be careful with your wrench when you're spinning it around. You hit that red lead over there with your wrench, you got mucho problems, right? That was a picture we had when we was in the Navy where they had a wedding band that was melted to a wrench where they was working on a band. We had a guy at U.S. Steel was working on a big, he was in electronics. The drives on all the forklifts and everything are electronic drives. You know, that sucker runs 24-volt batteries. It's probably got 5 or 6 of them in there. They don't tell how much current available. And he got in there with a metal watch band. And he touched it across 2 leads, and it literally fused that watch band onto his wrist and burned his wrist real bad. We had to cut that sucker off of him. And it was just solid where the watch was still working though. I don't remember what kind it was because it went around the watch movement. But, so we got to understand how we designate these voltages. So we got what we call VB, VE, and VC. These measurements are relative to circuit common. So if you see a designator that only has one letter, these are relative to circuit watt, common. And normally when we give voltages and we calculate voltages inside the circuit, we're going to calculate them relative to circuit common. Because that's the way I measure them. You get into one of these little old transistors, you know, these little TO92 cases. And it always bothers me. People think that when you measure voltage collector to emitter, you got to get your meter leads between the collector and the emitter. That's not necessarily true, right? You understand? I can measure voltage on the collector relative to common. I can measure voltage on the emitter relative to common, and then I can subtract the two, and that would give me the voltage collector to emitter, right? Does that make sense? Hopefully I can turn. Yeah, it's gone again. But look how close these things are together. And by the way, these are solid leads. And what's the problem with solids and being bent?
Break.
Yeah, they break. So what this means is we don't bend these leads up to match our circuit. The way you're going to put these things in is you're going to build your circuit around these leads. Man, I don't know where my integrity went. So I'll just have, there it is. So I'll have to do that every time I give. So what we're saying is that when I stick these things inside a breadboard, then we're going to stick them in just holes that are side by side. Oops. If I needed to zoom in. But all we're going to do is just take the transistors and stick them in 3 holes side by side, right? You understand that? And then you won't have to worry about bending the leads. And then we'll wire into the transistor. Can y'all see what I did? So I don't bend these things up. I see people do that all the time. They bend them up and bend them up. And then the next class comes in, they try to straighten them up, and they break the leads right off. So let me come over and find y'all torquing them things around to save a piece of wire. Because normally you got resistors and everything, you know. So, and by the way, you got these big, nice metal resistors, and they say measure on the collector, and you got a big old resistor over there with all this bare wire on there, right? You understand? That's connected to the collector, and you try to get to the collector lead when you could measure it where? On that big old resistor, right? Did switch back that time. Say, what's that? Yeah, but it's the integrity's not there. It's there now, but when I bring up my camera and I pop up my taskbar, the integrity thing is not there. So, yeah, I thought that's okay. We got to work through it. Voltages between leads. So this is a good slide. Voltages between leads are given the names of the leads, right? You understand that? Let me this will take a little while. This is the leftover last time I taught the class. There we go. So voltages, so VC, VE, VB. Now, of course, here VE is going to be equal to 0 volts, right? Later on, we're going to put a resistor down there, so it's not going to always be there. Then we got the voltages that we measure across the leads. And these are designated according to, so we call this VCE. So if we give you 2 voltages, they're going to be across something, right? We call this VBE. We call this VCE. And basically, they're giving you the math formula on how you take measurements relative to common and come up with those. So this is saying VCE can be calculated by taking VC minus VE, right? That makes sense? So they're basically giving you the formula that you use to to calculate them from measurements relative to common. Now, power sources are given their name depending on what lead they are connected to. That is not common. So right now we don't have a VEE because the emitter is what? The emitter is common. So this notice here, look at the difference. This says VBB. This says VBE. So if they give you two leads names, then that's the voltage across those leads, right? If we give you two letters that are exactly the same, then that's going to be relative to a power source. So this is connected to the base, and we call this what? VBB. This guy here is called VCC.
VCE. Is that a VCE? Right?
No, thank you. I missed. See, I just did that just to fill spaces. VCB. Yeah, because the emitter is usually, the base is usually less, and we don't want to come up with a negative number. So this would be equal to VCB. Because when I measure these two, I calculate it back like this. I see VCB would be equal to VC minus VB. VB, Rich. Because normally we don't measure between, we don't put a meter between the collector and the, we don't put a meter between the collector and the base. And why is that? You can short circuit real easy. But I can measure up on the emitter, so I could come up here and I could measure to this resistor lead right there, and that would give me VC relative to common. And then I could measure over here on that resistor lead right there, and that gives me VB. I subtract the two, and then that gives me VCB. So when we give you, the leads are telling you what measurements to subtract from each other to come up with these things, right? Here VE is smaller than VC. So VE will always be smaller than VC, the forward bias thing, right? You understand? Because as long as we're not saturated. But so what we're doing is we're taking the big and minus a little. So your VB is going to be about your base is going to be about 7/10 of a volt greater than the emitter. Not exactly, but it's going to be that. So this is going to be equal to approximately, if it's silicon, it's going to be always approximate to what? 7/10 of a volt if the transistor's turned on inside, if it's turned on, not necessarily saturated. Just because you measure 7/10 of a volt does not mean it is saturated. All it means is that it is on. And we know it is not going to be cut off, right? You understand? So if I measure 7/10 of a volt on the base, VBE, and then I measure my full voltage up here on my collector, then you might as well pull that transistor out and throw it away. One of your junctions are open. The base to emitter junction is okay, but understand we got 3 junctions that could be bad. I mean, not junction, we got 2 junctions that could be bad. So I could have a base collector junction could be bad, and I would still measure 7/10 of a volt between the collector and the emitter. But if the base collector junction is bad, then the transistor is going to appear to be cut off. So there's a lot of things we can troubleshoot a transistor, and we know it's bad just by measuring the bias voltages. And by the way, that's the way you determine if they're operating okay. If the bias voltages are where they're supposed to be. If they're not, then you troubleshoot it. If there are, then you move on, right? Because that's not your problem. The 3 DC voltages for the bias transistor reference to the 2 transistor leads, or we have voltage base to emitter, we have voltage collector to emitter, and voltage collector to base. And I just showed you how we got those, right? So here's my voltages collector to cluster emitter, voltages collector, and we got breakover voltages for all these too, right? But they'll say the other lead is open. So if you got one lead open, the transistor is definitely cut off. So what we're trying to do is we're trying to see what will break it over when the transistor's cut off. And that's going to be in all your bipolar transistor data sheets. You can break over between three leads. Power supply external voltages are designed with two-letter subscripts depending on the transistor lead to which the power supply is applied. Collector external voltages we're going to call VCC. Base external voltages is VBB. And then if the emitter is not common, then we can apply voltage to the emitter too, right? Everybody okay? Any questions here? So we got a lot of these designators that if you don't understand them, then we can't talk any further. Because we're going to VC, VE, we're going to calculate VB, we're going to calculate VC, we're going to calculate VE. We're going to calculate those three voltages, but we're not going to designate them. We're going to just call them VB. We're not going to call them base voltage, right? You understand that? We'll call them that. Voltage collector to emitter, voltage collector to base, voltage base to emitter. And then the power sources. So if you see two letters that repeat each other, they're not different, then we're talking about power supplies, right? Everybody okay? So let me give y'all a beta. What we're going to do first is we're going to calculate absolute. We're going to consider beta to be a fixed value. And beta would be a fixed value if the transistor was operating at a fixed temperature. So let's use, just to make sure we don't saturate this thing, let's use a beta of 100. Okay, somebody tell me where I need to start at. First of all, what type of transistor is this? Right, NPN. Do I have a positive on the base? Yes, I do. Only 3 volts though, right? Do I have a positive on the collector? Yes, I do, but it's a lot more positive than the base, right? You understand there's 20 volts available on my collector power support. There's only 3 volts available on my. So the transistor has the ability to be turned on. Is this voltage right here greater than 0.7 volts? So this guy here is turned on, right? Now we got to figure out what region is it operating in. Okay, so what's the next thing I'm going to do? Anybody got any ideas? We got to calculate a current, right? Which current can I calculate right now? Not current I. We're dealing with I. What current can I calculate? Base current, collector current. Base current, because I know this right here. I know this right here is 0.7, right? You understand if it's silicone. If that's 0.7, then I know what that resistor drops. What's the resistor going to drop? 2.3 volts. Does everybody understand where that came from? Yes or no? Yes or no? Everybody okay? Kirchhoff's voltage law says, so I have a series branch right here. I have a series circuit right there. Kirchhoff's voltage law says the sums of the voltage in a series loop has to equal to the applied voltage. I know my diode is forward biased. How do I know it's forward biased? Because the P is pointing toward a P, and the N is pointing toward the N of the source. So I know it's forward biased. If it's silicon, I know it's going to drop 0.7 of a volt. So I got 3 volts applied. So this is my circuit right here. And we've done this several times this term, right? I got a 3 volt supply. Over here I got a resistor right here. I got a diode that is forward biased. How many times have y'all calculated this and screwed up with it on the test? We got two tests that I could guarantee you, and it's forward bias. So if it's forward bias, this guy right here drops about 7/10 of a volt. Kirchhoff's voltage law says the sums of the voltage have to equal to the applied voltage, right? So what's it going to drop? Well, that means this guy right here's got to drop what? Got to. Now, of course, now I know I can calculate. Are you okay, tomorrow? Okay. Now I know I can calculate what? I can calculate IB. How can I calculate IB? Huh? Well, I know the size of RB. If I know the size of RB, I know the voltage drop across RB, I can calculate the current flow through RB. And it's a series circuit. What's the same in a series circuit? Current. So it means if I calculate this current flow through this resistor, I've calculated the current flow through the base to emitter junction, right? Y'all understand that? So IB is going to be equal to 2.3 volts divided by 10 k ohms. So what's IB going to be equal to? And that's IB. How do I know it's IB? You say, wait a minute, Rich, that's not IB, that's IRB. But IRB and IB are what? They're the same. Why? Because it's a series circuit, right? Okay. So now I got to move over to the other side. I have no idea what the ohm value of the transistor is. But by George, I have, if this beta is constant, which is what we're dealing with now, just to learn how to play around with it, then I know I can calculate IC. So IC is equal to IB times beta. So IC would be equal to IB, which is 230 microamps, times 100. That 100 has no units. It is a multiplier. So IC would equal to what? What's that? And we messed up. Huh? Well, sort of. So we'll see what region. We'll change the beta. Everybody okay with 23 milliamps? We can't have 23 milliamps flow. Yeah, why? Can anybody tell me? So I got 23 and we calculated 23 milliamps of IC. Okay. So if IC is flowing through the transistor and flowing through RC, I don't know the resistance of the transistor, but I do know the resistance of RC. So I say VRC would be equal to IC times RC. VRC would be equal to 23 milliamps times 1K. VRC would be equal to what? VRC would be equal to 23 volts. What's the problem? Yeah, we've only got 20 volts to work with. You can't drop more voltage in a circuit than what you have applied to it. Unless you take AC. You haven't had AC yet. But there's a reason in AC it's just not true. But when you get into AC, how many people said AC? So how many volts would RC drop? RC would drop around 20 volts. And what would be our voltage collector to emitter? Kirchhoff's voltage law says the sums of the voltage drops in a series circuit have to equal to the applied voltage. I come up here, I got 20 volts drop right there. How much voltage would be left over to drop across the transistor? Yeah, 0 volts, so the transistor's saturated. Of course, this is not going to be true. Transistor's going to drop less than a volt, and then the rest of it's going to be a drop across your resistor. So if you calculate IC, and you multiply it times your collector resistor, and you come up with more voltage than is applied, y'all understand we cannot drop more voltage than is applied in a circuit. So the transistor is saturated. So let's redo that. I'm going to go to a lower beta. So let's do a beta of 50 and let y'all recalculate it. So we got one answer of 8.5 volts. Any more? Millivolts. Any more? Okay, gang, y'all go ahead. We'll go ahead and work this as a class. So the first thing I would do is I would say that this resistor here, RB, is going to drop about 2.3 volts, right? Everybody okay there? Then how do we know that? Because it's in series with this base emitter junction, and it's dropping 0.7 volts. So I can calculate IB. So IB would be equal to 2.3 divided by 10K. And we already got that, so that would be, what, 230 microamps. We hadn't changed that side because that side, the base side, has nothing to do with beta, right? You understand? So you okay so far? Then IC would be equal to 230 micro times 50, which is the beta that I gave you. So what would IC be equal to? Yeah, 11.5 should be half of what we had a while ago. Some of y'all could have calculated this in no time, right? Then VRC would be equal to 11.5 milli times 1K. So VRC would be equal to 11.5 volts, which is not voltage collector to emitter. That's the voltage drop across that resistor, right? You understand? So what I have, and all of this is, you know, I don't know how many of these circuits like this you worked in DC. which I guarantee you worked a few, is we got one circuit over here controlling the circuit on the other side. So this is RB. Here's my transistor emitter to base, and that's that circuit right there. I've been drawing it as a diode, but I'm going to draw it like this from now on because it's not a diode, it's a transistor. Right? We know this guy here drops approximately 0.7 of a volt. It's not exact, but it's close enough. Then I know my second circuit over here is this circuit right here. Here's RC. Here's my transistor. And here's plus 20 volts. Now what we just did is we calculated the voltage drop across this resistor. This resistor came up and gave me 11.5 volts. That is not the voltage drop across the transistor. That is the voltage drop across that resistor. Now what law would I use to calculate? So here's voltage collector to emitter right there. And that is the voltage drop across the transistor. Kirchhoff's voltage law says the sums of the voltages in a series path has to equal to the applied voltage. I got 11.5 volts dropped on one resistor, so why much does the other one have to drop? So voltage collector to emitter would be equal to 20 minus 11.5. My voltage collector to emitter would equal to what? 8.5. Now, you only learned one new formula, and it's not that hard. All it is gain. You know, and we're going to deal with gain a lot this semester. We're going to deal with voltage gains, we're going to deal with current gains, and we're going to deal with power gains. Of the three, of course, power is the most important, right? And that's all beta is. It's just a gain. That's all it is a gain. It tells us how much we gain on our collector current compared to our base current. That's right, because it's a series circuit, right? We know the transistor is forward biased because we have a positive on the base. We have the negative is pointing toward the emitter, and we know we have a big voltage on the collector, right? VCC is big, and that's what we're trying to forward bias the transistor. A PNP, we got to have this. So the base has got to be, since the emitter is common, then the base has to be positive in respect to the emitter. But no, I got a little old tiny positive there because it's going to only be about 0.7 of a volt, right? And then the collector's got to be more positive than the base emitter junction, because what we're doing is we're sucking those majority carriers through the base, right? So it's forward bias. I mean, I got a 20 volt collector power supply. And I got a 3 volt base power supply. First of all, to turn it on, the base power supply has got to at least be what? Got to be greater than 0.7 of a volt. If it's equal to exactly 0.7 of a volt, the transistor is not really on and the transistor is not really off because you have no base current. Because if you say 0.7 of a volt to drop across the transistor, how many do you have dropped across that resistor? None. If you have no voltage dropped across your base resistor, you have no current. So we got to have more than 0.7 of a volt to turn the transistor on the base voltage. Y'all realize all that I just said? You understand that, right? So do we have greater than 0.7 of a volt on the base? Sure. We have 3 volts. Do we have greater than that over on our collector? Sure. So we're fine. And we treat this like 2 series circuits, which is pretty neat. Well, the series circuit on the left that's controlling the series circuit on the right. But besides then, so what is gain? Gain is out divided by in. That's all it is. How much you get out by what you put in. That's gain. Right? Y'all understand? And that's what beta is. Beta is the current gain with the emitter common. That's all it is. HFE. And besides for that, it's all Ohm's law and Kirchhoff's law. That's all it is. It's Ohm's law and Kirchhoff's law. And you could, I'll give you a formula sheet out, but I understand this is nothing but laws. You didn't, right now I shouldn't even give you a formula sheet because this is nothing but what? Ohm's law and Kirchhoff's law. If you don't know Ohm's law and Kirchhoff's law by now, then you got problems. And we drawn y'all this, right? So we got the base emitter controlling the collector current, and we calculate the collector current by taking beta and multiply it times the base current. And we've already done that, by the way. Here's your formula. The only new formula is this guy right here. All the rest of it is stuff you did in DC. And that's really not a new formula. If I wanted to calculate my percent range, I would take what I'm making now, I would divide it by what I made before, and that would give my percent range. It's a gain, right? You understand? And why do we calculate gain? By the way, gain, we represent this by the letter A in formulas. And gain is always equal to out divided by what? In. So we come up here and put A little d, and guess what this will be? This will be a voltage gain. And then, of course, A little I would be a current gain. And then A P, little p, would be power. So formulas will represent gain. All gain is what? Out divided by in. So a voltage gain would be your output voltage divided by your input voltage, right? Current gain would be your output current divided by your input current. It's just that beta is a specification given for a transistor. We'll use these gains later on when we start dealing with amplifiers. So here you go. Y'all calculate this. Wait a second. 100 ohms. We can use the other one. That was 1,000. Let's use a beta of 100 here. I don't have my calculator here, so I can check it real quick. Now do. So let's. Yeah, that'll be fine. For this voltage collector to emitter. Now, why are we looking for this is that this determines the region that the transistor is operating in. If voltage collector to emitter is less than 1 volt, we consider this transistor to be saturated. If voltage collector to emitter equals to VCC, we consider the transistor to be cut off. If voltage collector to emitter is greater than 1 volt, right, but less than VCC, we consider this to be in the active region. And what we're trying to do is put it right in the center of VCC, and we'll talk about it later on. So this guy here is definitely in the active region. Okay, so what we got for VCE? 7.7 volts. 5.7. Any more? 7.7. I'm sorry. You did say 7.7? Okay, any more? So we're dealing with voltage collector to emitter. We're going to work it. I mean, it's just, we're going to work it, but what we do is get answers first, right? You understand? So here I'll start off by calculating RB. So RB is going to be 4.3 volts. I didn't have to use a math formula to do that. I can do that in my head. I just subtract the 7/10 of a volt from 5 volts, right? Take 7.7 off, right? Which is pretty neat, pretty easy. Of course to me, but I teach it, you know. Then I calculate IB. So IB would be equal to 4.3 volts divided by that nice 10K, which is pretty nice because that means it's 430 microamps. Uh, 100 microamps per volt with a 10K. It's 1 milliamp per volt for a 1K. So those guys are really, really neat. So 430 microamps. I didn't even pick up a calculator so far. So IC would be equal to 430 micro times 100. So that means IC would be equal to 43 milliamps. We okay so far? Okay. VRC would be equal to 43 milli times 100 ohms. So what we got for VRC, I'm sorry, not VC. We got to get these designators right. If I make mistakes on them, I'm going to really have problems. So VRC, they still make roll colas, RC colas. Don't remember RC. VRC, 43 milli times 100, so VRC would be equal to 4.3 volts. Then voltage collector to emitter, voltage collector to the emitter would be equal to 10 volts minus 4.3 volts using Kirchhoff's law. What does that give me? 5.7 volts. So the problem we have is people see this sucker and they get scared because we got this symbol up there for a transistor. But if you come up there and treat the dang thing like two series circuits right here. We got this circuit right here. There's RB. That's one series circuit. All right. Then we got this other series circuit. I'm gonna put the power supply on this side because normally. Then I got a resistor right here. Here's RC. I got a resistor right here. Here's RT. And the problem with RT for the transistor is that it's long. It could be anything. But that RC up there is not. It's a fixed resistor. So that's what we work with. And what I do is I take the current here. So I take IB. So IC is equal to IB times what? And that's what connects the two circuits together. And of course, IC is the collector current, and it's in parallel. So what we're assuming, of course, is we're assuming that IC and and we're assuming that IE, we're not using IE.
Question, DC versus on the line. But if you like the voltage that you use,
That's exactly right. Voltage, collector to emitter. Now here's VCE, here's VC right there. VCE, voltage collector to emitter, is the voltage drop across the transistor. Now why is that important and why we're going to calculate it every time? Because this determines the region that the transistor is operating in. So we calculated 5.7 volts. Is that less than 1 volt? Is it equal to 20? So it's somewhere between 1 volt, it's greater than 1 volt, less than VCC, so this transistor is in the active region. So it's acting like a rheostat. A while ago, when we got more current out than we could, it was acting like a closed switch, right? Now here, we say we calculate it, where we come over here and we say voltage collector to emitter would equal to the voltage on the collector minus the voltage on the emitter, right? So here the voltage on the collector would be equal to 5.7. The voltage on the emitter right now is equal to 0. So voltage collector to emitter would be equal to what? 5.7. Later on we're going to put a resistor in here. Not right now. To keep the thing from going into what we call thermal runaway. So I'll hook this up and I'll see if we got these size resistors. I'm pretty sure we do. And we'll use a 3904 our calculations. So what we'll learn is we'll learn a typical beta. 3904 typical beta is around 100. So we can hook this up pretty good. But what's going to happen is I'm going to get a heat gun or a soldering iron and put it across this, and you'll notice that the voltage drop across the collector to emitter goes down because beta changes with temperature. So if temperature goes up, the beta goes up, which means IC would go up. IE would go up. If IE goes up, then RC is going to drop more voltage, and the transistor is going to drop less, right? You understand that? And we might be able to saturate this because the beta could get all the way up to 300.
how did you more game? You said you got the beta game.
That's true.
I thought more temperature would be more.
No, you're thinking about a piece of wire. This is not a piece of wire. The temperature of metals go up. The resistance of metals go up. But here we're dealing with a current that's controlled by majority carriers. And what happens is when you heat electrons up, they become more active, right? You understand? Which means they release more majority carriers, which means the beta goes up. So in a transistor, it's not a piece of wire. Right? You understand? Now metals, if you heat metals up, what happens to their resistance? Their resistance goes up. But this is not a conductor. It's a semiconductor. And semiconductors, it's just like when we got in there and put our reverse bias, that little 914, 1N914, we broke it over at about 104 volts. And then we put a little soldering iron up against it, and all of a sudden, it started conducting more current, right? You understand? Because now we're dealing with a semiconductor that the electrons become more active, right? Yeah, so beta goes up when you heat it up. And what we're going to try to do is so I couldn't happen that in stereos, right? I got to do something to not deal with that. I got to do something because your radio would saturate in the summertime, right? You understand? You get all kind of distortion, and then you either design it to run in the winter. If you design it to run in the summer, and then you run it in the winter, you can't get near the gain out of it, right? You understand? So we're going to learn as we go along how we can ignore this change in beta. We're not going to ignore it. We're going to make it where it can't change with temperature. And we're going to do it with resistors, because that's what resistors do. What is resistors? They control current. So if I've got some way I can use a resistor to keep beta from changing, then we're going to do that. And if I can keep beta from changing with temperature, then what can we do? Then we can operate the amplifier over a wide range of temperatures. But we got to learn this first before we get there. So anymore, it's a good question. We'll try to get to the switches, and then we'll be in lab all day Wednesday. Just because we're in lab is not an excuse to be late, right? Okay, let me think. First of all, this is basically the first circuit that you're going to hook up or connect. And we have two power supplies on the trainer. But the two power supplies on the trainer are connected like this. And then this is our little terminal block right here. This is our little terminal block right here. And then this is the one labeled ground. And this is going to be the banana plug jumper over there. And so when you look like this, when you look at this, it's going to be impossible to hook up this circuit with the power supplies that are on the trainer. Because your negatives need to be common, but when I look at this, so this would be the positive supply, this right here is the negative supply. And here it's the negative on the positive supply is common to the positive on the negative supply. Y'all see that? So that means I cannot get this circuit right here from the two power supplies on our trainer. So what does that mean? Jonathan already knows because he set this up. What does that mean? But you can't. It's wired into the trainer. Are we going to take the trainer apart and rewire the power supplies? We cannot do that. You got to use an outside power supply. So you got to use. You can use one of the power supplies on the trainer. It don't make any difference which one you want to use it for. But you're going to have to use a secondary power supply that you're going to have to connect up. So we got these big nice power supplies right here, these metal ones. They're stacked up in here on this table, and you can get you one of those. And then what you're going to do is you're going to calculate. You're going to use RB to calculate your base current. You're going to use RC to calculate your collector current, right? You're not going to use a current meter. And you're going to find out that the current meter, the actual true current meter, is probably the less often used meter of your three that you got available on your available that you got. Sorry, I don't think it's Nancy. It is Nancy. I'll call her. I'll call her back. She knows better than to call me during class. Well, it's just important she would text me. Of course, she might have already done that. And that's what you're going to do. And we'll look at see what you're going to do with that. Okay, so y'all understand what you're going to have to do. So one of your power supplies is going to have to be an external power supply. We got plenty of those for the class. If we run out, y'all can use mine up here. But I think we got plenty. And we got We got boxes of these, by the way. Some of them hadn't even opened yet. So transistor is a switch, but so y'all understand what a transistor switch is. So what are we going to do on a transistor switch? Switch it between cutoff and saturation, right? Okay, y'all take a 2-minute break because I constructed this circuit. And, what's neat about this one is that it's got a 5-volt supply, and we have two supplies. We have three supplies on this one. We have a plus and minus supply, variable supply, and then we got a 5-volt supply, and them suckers are isolated from it. The 5-volt supply is isolated from the variable supplies. So what I've done is so I've connected the blacks together on the 5-volt supply, which is on this side, and the variable supply, which is on that side. And then here's my transistor circuit. I need to get this guy here out of the way. My camera here real close. So here's the transistor circuit. So here's my transistor. This is a 2N3905. The emitter's on the left. If you look at 3904, the emitter's on the left, and then the base is in the center, and the collector's on the right. So if I can get this to focus. This is a 10K resistor, brown, black, orange. This is a 100 ohm resistor, brown, black, brown. Brown, black, brown. I have this one. Here's my 5-volt supply right there. This is connected to the base. Here's my 10-volt supply, and then that's connected to the collector. And what was the voltage we calculated on the collector? Collector to emitter? This is not the, so that was depending on a beta of 100. So when I look at this one, I measure my collector, and it's measuring. So there's the power supply. So it's measured 4.8, which is not bad, right? You understand? We calculated what? 5.7, so we're off about a volt. Okay. Now what we're going to do is, I've got this guy right here, and this is a heat gun that we use to heat shrink with. And what I'm going to do is I'm going to look at the collector voltage, which is the collector to emitter voltage, because the emitter is connected to ground, right? You understand? So I'm going to come up here and start heating up my transistor. What I'm going to do is I'm going to take my red lead, I'm going to put an alligator clip on it, and hook it to my collector. So it is, that's 4.8 volts. So if this voltage starts dropping down, that's because the voltage drop across my collector resistor is going up, right? If the voltage drop across the collector resistor is going up, the only way it could be going up is IC is going up. And IC is controlled by beta. So you can see it starting to do what? I don't want to melt my breadboard. This thing right here gets hot. I need a solder knife. Guess what I'm doing up here. I'm melting my breadboard. Yeah, when it started going the opposite direction, I said what's going on. Huh? breadboards are nice and shiny now. So when we first put it on there, it started going down, right? Dang it. Still pretty warm. Okay, there we go. So notice as it starts heating up, then what's happening? Voltage drop across the transistors going down. If the voltage drop across the transistors going down, then the voltage drop across the resistor must be going up. I don't think I've destroyed my breadboard bad enough for it to. Now eventually we could probably cause the transistor to saturate. See what's happening? So we started off with 4.8 something, now we're down to 4.7 something. Well, you can see the 7.3, which is what's important here. And just when I let it off, it went back to 7.3. Now I'll have to heat it up again. I can touch this. We got plenty of these. So the problem is when we start dealing with beta, we have a problem with temperature, right? You understand that? So if the temperature goes up, then what happens to beta? It goes up, yeah. And if beta goes up, then IC goes up. If IC goes up, then the voltage drop across the transistor is going to go down, and then the voltage drop across everything else is going to go up, right? Because the amount of IC you have determines the amount of resistance that the transistor has. So you want to see my burn up board? Yeah, nice and shiny. Oh, yeah, you can't hardly see it. It's still in good shape, but I got it off in time. And what was so funny, I just got through telling y'all I was gonna. So let's say we wanted to design a switch, a transistor switch. Well, the problem is when I look at my beta load in the collector, and we'll talk about why. But normally it will come up here and we'll put the load in the collector. So let's say we wanted the transistor to turn on a light bulb. Let me find a blank. I think I got a blank sheet up here somewhere. Oops. So what we would do is we would come up with some way. What do y'all want to turn it on with? First of all, we'll just start off by using just a switch. We don't need that resistor anymore because the The light bulb itself is the collector resistor. Sorry, I was using the wrong marker. Okay. My integrity is giving me problems there. So we don't need the collector resistor. And then this would be our collector power supply. See, okay. So right now, if the switch is open, the transistor would it be cut on, cut off, or would it be saturated? Cut on, active, would it be cut on, cut off, or saturated? Huh?
I'm saying second.
Okay, so saturated means it acts like a closed switch. Because you have no IB. If you have no IB, what would my IB be equal to if the switch is open?
Cut off.
Yeah, so we're cut off, right? Y'all understand? I have no IB. If IC, which is controlling my light, if IC is equal to IB times beta, right? You understand? And then IC is going to be equal to 0 times beta, so IC is going to be equal to what? 0. So the transistor's cut off. Let's say this right here is 20 volts. And of course, right now, if I measure it across my light bulb, what would it measure? What? What would it measure? Huh? What would the voltage across the light bulb be?
Is that a resistor?
Don't make any difference. What would the voltage drop? No, I cut the resistor off. Still don't make any difference. Now let's see. V across the bulb is equal to the resistance of the bulb. So let's say it's 100 ohm. Times the current through the bulb. That's equal to 0 because I have no IC. So I mean voltage across my bulb is going to be equal to 0 volts. I mean, this is, folks, this is basic stuff. This is basic stuff. So 0 volts across my bulb because the transistor is acting like an open switch. All the voltage drop is across the transistor. It's across the open element in a series circuit. If I had voltage across the bulb, then the bulb would be doing work. The bulb's not doing any work because it has watts not going through it. I mean, I just don't get work. What do I have to do to get work? So my transistor's doing no work. So what do I have to get work? Okay, current. But I can have current and no work. So I can go over to that light switch over there and I measure 0 volts across it. Well, power is equal to V times I. So that's 15 amps times 0 volts, right? How much work, electrical work, does a light switch do? It does none. Right? You understand? It's not supposed to. It's a device. It's a device that controls, it allows us to control the current, but it does no work. Should be working now, Nancy. Okay. So to get power, I got to have power is equal to what? Power is equal to what? Okay, that's one formula. So I can have current without voltage, or I can have voltage without current, and I have no work. So that means the transistor's dropping 20 volts. Is the transistor doing any work now? Yes or no? It's dropping 20 volts. But it's an open switch. 20 volts times 0 current is still no work, right? You understand? And that's what a switch does. It either conducts current or it don't conduct current. Now the transistor is going to do a little work because we can't saturate it. And then we got power is equal to I square R. But we still have to what? Have to have current through resistance. And then we have power is equal to V squared over R.
You also think that's open switch, right?
Yeah, but what we're doing is we're using this little tiny switch. This could be a little tiny switch. Because all it's got to do is drop this voltage right here. All it's got to do is drop that voltage by the current that needs to flow through that resistor. And what determines the size of a switch? Two things determines the size of a switch. Huh? The current. Now, powers don't do power. Switches don't do watts. Switches do not do watts. Okay, so amps, current. So when I close it, we get current. When I open it, it's got a block of voltage, right? You understand? Just like fuses. Fuses are rated in amps and volts. Because when they break that circuit, that voltage is trying to do what? It's trying to push that current through an open. Right? You understand? Well, when it breaks, we call it blowing for a reason. So it creates this ozone arc inside there. And then now, if we don't do something, current can conduct through that ozone, right? You understand? So fuses and switches are rated in current, and they're rated in how much voltage they can block when you turn it, when you open that switch up. So when you go down to Lowe's and buy a light switch, look at there, it's got 125 volts, 15 amps or something like that on there. So they guarantee you that switch can break at least what? 125 volts at that current. So that means I can't go down to Radio Shack and buy this little old tiny switch that's rated at 12 volts and try to control a 115 volt circuit because it's not guaranteed to break, right? You understand that? Because that power, that voltage is trying to do what through that switch? It's trying to push that current all the time. So here we're dealing, that switch right there, we're dealing with very little voltage, very little current. So this is going to be a little old tiny thing, right? Could be a photocell, could be all kind of neat little things. So my transistor is rated at a voltage and a current too, but it's rated as a power and all. It's got other ratings too. So here we're concerned with that current, that IC current that it can handle. And then we're concerned with how much it can block collector to emitter when we do what? When we cut it off. So that's what when we do saturated switches, that's what we're turning. And we're not really concerned with the power rating of the transistor because when it's saturated, it's almost producing no power, right? You understand? And when it's cut off, it's producing no power. So we worry about the power rating when we operate the transistor in the active region. Okay. So what would I need to do to design this thing? First, what would be the first thing I need to know?
Calculate RV resistance.
Yeah, we do, but where do we start at? Well, we start at the load. We start, okay, what do I need over here on my load side, right? You understand? Okay, so I need something on the load. So we say that transistor is 100 ohms. So what do we need to turn it on? Not dim it, turn it on. So what current do I need to turn it on? Well, I'll say it's going to drop. When I saturate the transistor, it's going to drop how many volts? Not a collector to emitter. It's going to drop 0.7 on the base, but we're not talking about this guy right here. This is my current. This is my circuit. This is my circuit. If I can get it to pop back up there. So this is my circuit right here for that light bulb. So what we're trying to do is we're trying to do this circuit right here. I got a light bulb, and I got a switch. My transistor is the switch. We're not operating in the active region. We're going to operate this sucker as a switch. Then over here I have a battery, a DC source, that's equal to 20 volts. If the switch is open, which means the transistor's cut off, which is what it is now, then how much voltage is across the bulb and how much voltage is across the transistor. So this is the circuit I have right now. How much? No voltage across the bulb because there's no current flow through it. So it's not doing any work. All the voltage is across the transistor, and it's not doing any work because we got voltage without current, right? You understand that? Okay. So I come up here and I close this switch. Well, as soon as I close that switch, if we calculate this right, that's going to close that switch. How much voltage drop across a closed switch? None. Good, thank you. None. Right? Now, the transistor is going to drop around 200 millivolts, but we're going to ignore that because what's 200 millivolts to 20 volts, right? You understand? So I'm going to say all my 20 volts is going to be dropped across that light bulb. And that light bulb has 100 ohm worth of resistance. So how much current would be required? Huh? Around 200 milliamps. So we're going to call this IC sat for the saturation current required to turn that bulb on. This is going to be equal to VCC divided by. Now, what's nice about light bulbs is light bulbs are usually rated at a current or they're rated at a wattage, right? Do you understand that? If they're rated at a current, you know, you go out and buy a little bulb for your flashlight, it's going to be rated at a voltage and a current. You buy a bulb for your house, it's going to be rated at a voltage and a wattage, right? You understand? And then you can calculate the current by knowing the wattage, right? So I is equal to P over V. Here I'm giving you the resistance. So my saturated current would be equal times the resistance of the bulb, which we'll call bulb. So this is going to be equal to 20 volts divided by 100 ohms, which is 200 milliamps. Okay. Huh? Yeah, I give you the 100 ohms. I gave you the 100 ohms. I just didn't put ohms out here. But I could have gave you the wattage of the bulb. So it was a 20 volt bulb. By the way, bulbs are rated at a certain wattage, but that wattage is going to be at a certain voltage, right? You understand? And incandescent bulbs have a resistance, but you can't measure it with an ohm meter. If you measure with an ohm meter, you're going to get an extremely low resistance because it's made out of metal. The filament in there is made out of metal, right? You understand? And metal heats up. When it heats up, that's where you get the resistance of the bulb. So that's why most light bulbs blow when you turn them on. Because if there's any deficiency inside that element and you turn it on and you pop that thing with almost no resistance, it takes a short amount of time for the resistance to build up. Have you noticed that? Light bulbs usually blow when you do one. You turn them on, or when you bop them real good. They'll turn real bright. Because what happens, you make those little filament springs bounce, and the two of them touch together, and they're white hot anyway. What do? They just fuse, and then you change the resistance. Okay, now what I need to do now is I need to calculate IB. So how would I calculate IB? Well, that's what we're trying to do. We're going to calculate IB going backwards, right? No, we don't know the size of the resistor. IB. I know that IC is equal to beta times IB. So what would IB equal to? Good. So IC over beta. So now that, okay, y'all follow it so far. The problem is that I have to deal with a beta. So here's the beta on 3904. So what beta am I going to use? It can be anywhere between from 30 to 300. What beta am I going to use? Which beta is guaranteed? The 30 or the 300? The 30 is guaranteed, right? In other words, once we saturate a transistor, it don't hurt to put more current than requires to saturate it. Don't hurt at all, right? So the 300 is not guaranteed. The only beta that is guaranteed up there is the 30. Y'all understand that? So that means if I use a beta of 30, then that beta is guaranteed. Y'all follow that? So let's come up here and we'll come up here. Where's my slides at? If it comes up. Let's see if it comes up. Here we go. So I'm going to say 200 milli divided by 30. And we're going to call this IBE sat. So what's my saturated base current that I need? Everybody okay? So we're sacrificing a lot, but I'm still only using 6.7 milliamps to control 200 milliamps, right? You understand that? So my little old switch over here can be rated at 6.7 milliamps to control that 200 milliamp that's required by my light bulb. Okay, so what size resistor would I use for RB? Let's see, Ohm's law says R is equal to V over I. So what V are we going to use? Now we're going to use 4.3. Even though this situation 5 would hurt. Divided by 6.7 milliamps. So we can hook this puppy up. I don't know. I don't know my light bulb. I have to measure the current on the light bulb. This little light bulb I got is no way in the shape or form a 200 milliamp bulb. In fact, I don't even know what it's rated at. So what size do we calculate for RB? Huh? What's that? What's that? No, there's no such thing as a 641.8 ohm resistor. Huh? Now we could make this with a rheostat, right? But I'm going from a component that a standard resistor might cost me $0.25, if it's that much. A rheostat that would do this would probably be around $5. So which way would we go? Standard resistor or rheostat? So now I got to decide which way am I going to go with this. Am I going to go up or am I going to go down? Yeah, we're going to round it up or we're going to round it down. Corey says down. Huh? Well, think about it. If you round it up, IB is going to go down. If IB is going down, then beta's going to go. Right? You understand that? We're trying to make sure this thing saturates. If I use a resistor there that's too big, then saturation is no longer guaranteed. Y'all understand? Because if I use a bigger resistor, that means I've got to depend on a bigger beta. Well, the bigger beta is not what? It's not guaranteed. So we always round this down. So what size would I use? Y'all got that standard resistor chart there on? Y'all should have it. Yeah, it's on Blackboard. But I got it here somewhere. We calculate 640, something like that. Standard resistor values. 0.5, you can't, like I said, you can't get to 10s anymore. You'll never find a 20 unless it's in a circuit. So a 20% has no tolerance band, right? So we say it's a transparent. So I would, 620 might be okay. I'd multiply that by 1.05. I'm sorry, I'd divide it by 1.05, right? No, that's right. I'd multiply. I multiply by 1.05, see if it came up to be greater than 640. If it does, then we'll go down to the next standard. So it's just like the Zener. Same technique you use for the Zener. Because Zener, you're trying to move it down, you're trying to move it greater than the knee current, right? You understand? And this guy right here, we're trying to make sure that we at least maintain minimum beta. Because anything above 30 is what? It's not guaranteed. So if we use this, and I use, so what size resistor did we come up and get? Was 620 okay? 560. So if I use 560, this guy here would saturate in Alabama, it would saturate up in Alaska, it would saturate on the North Pole or the South Pole, it saturate here, or it saturate in Australia, you know. We was on an island, Diego Garcia, when I was in the Navy, was 3 degrees above the equator. So I crossed the equator about 4 or 5 times. And the thing was, when you're above the equator, the commode's flush, it spins this way. When you're below the equator, they spin that way. So that wasn't true, by the way. So how can you tell if you're above and below? Depends on which way the commode flush was. Go ahead. Huh?
You said they wasn't cool, it didn't make a difference.
What's that?
They said they wasn't cool.
No, I'd say it wasn't true.
Oh, okay.
Yeah, when we was on Diego Garcia, there was a woman behind every pine tree. Guess what? There wasn't any pine trees on that island. None. Of course, it's changed a lot since I was over there. I was over there when they was building up the base, but a little old tiny island out in the Indian Ocean. So let's see if y'all can do it. What I'm going to do is integrity's messing up, so I think it's recording. I hope so, because we got several people that's not here. So what you want to turn on? Huh? We can turn on a sprinkler system, but we'd have to do it through a relay. So this is a symbol for a relay coil. Y'all understand relays? They're really, really neat stuff. What's nice about a relay coil is that we can control the solenoid with like DC, but the contacts could be controlled in what? AC, which usually, because what advantage does DC have over AC? Electronically. We can control AC, but it's more of a turn on, turn off type situation with AC. Sometimes we have some analog controls like light dimmers and stuff like that. But DC, we can control that thing electronically. So transistors can't control AC. But transistors can control DC. Transistors can produce AC, but they can't control AC. And we'll show you how we do that. Anybody got an inverter you buy for your car and plug it in? Yeah. My wife's fan's got that in there. So what we can do is, these, by the way, this is a symbol of a relay contact. And then this can be controlled in the solenoid that is turning on my water sprinkler. So that's the symbol for a solenoid. And then over here, this right here could be AC. So I got my little transistor over here. I saturate it. It energizes the relay. Relay closes the contact. Contact opens up the solenoid, lets the water flow through, and now my water sprinkler's up there going. Now we got to know two things about our relay. What's the two things we need to know about our relay? We need to know the current that it's rated at, and we need to know the voltage that it requires. So relays are rated in a voltage and a current, right? Or they'll give you a voltage and a resistance. A lot of relays are rated in a voltage and a resistance. Then you can measure it with an ohm meter. So let's say it's 24. Let's say it's a 24 volt relay coil. This is what you run into in your house. 24 volt, and let's say it's got a resistance of 200 ohms. And it's a DC coil. So that means my power supply up here that I'm going to connect this to is going to have to be plus 24 volts. Pretty simple, right? When you're operating a switch, a transistor as a switch, we just use our power source is just whatever the load requires. And you can go out and buy a 24 volt DC power supply. It's pretty simple. We're going to do something a little different here. We're going to control this off a single power supply. So what I'm going to do is I'm going to come over here. Because very seldom do we run something off two supplies, right? You understand that? So I'm going to come over and put a resistor right here. And then we're going to change the operation of the switch. I'm going to come over here and do this. So if the switch is open, then the transistor should saturate. If the switch is closed, then the transistor is going to cut off. Do y'all understand why? Because when I close the switch, I'm connecting my base and my emitter together. If I connect my base and my emitter together, I cannot get VB. VB is going to be equal to 0. If VB is equal to 0, then the transistor is cut off, right? When I open the switch, then we're going to size this resistor right here to drop 23.3 volts. And if I size that resistor to drop 23.3 volts, then we're doing the same thing we were doing before, but we're doing it now with how many power supplies? One. So this is the way we usually do it. Very simple circuit. So if the switch is closed, then we're going to have to make sure that the switch can handle the current, because now the this resistor up here is going to drop 24 volts, right? You understand that? Okay. So what do I need to know now? Still can't do anything. The beta. So we'll use a 3904. So I'm going to use my minimum beta. The minimum beta, we looked it up, is equal to 30. So you should have everything. You should be able to design your own transistor switch. So somebody tell me, what's the first thing we're going to do? We're not concerned with the transistors cut off. We're concerned what goes on when the transistor cuts on, right? You understand? So how much voltage are we going to say the transistor drops when it's cut on? If it's a switch, if it's acting like a saturated switch. Yeah, we're going to assume it's going to drop 0 volts, approximately 0. It's going to be a little greater than 0, but it's going to be less than 1, right? And a 24 volt relay would work fine on 23 point something volts. Okay, so what are we going? We need to calculate this thing we call IC sat. So how do we calculate IC sat? Don't need beta yet. I need to calculate the maximum, the current that I need through that relay up there. So I'm going to say 24 divided by 200 ohms. So what you got to understand is we're applying Ohm's law to a circuit that is dynamic, right? You understand? We determine when it's on and off, right? We get a current gain out of that transistor. So the switch that's controlling the current does not have to carry. It is not carrying the load current. The transistor is. So what do we get for IC sat? What do I say? Is everybody okay there? Okay. Now I need to calculate the base current. This comes with what we call the gain formula, which we call beta. So IB would be equal to IC divided by beta. Here we're using the minimum beta. Because why are we using the minimum beta? Because it is guaranteed. 300 is not, but 300 is. 30 is. So that means no matter what condition we operate this guy in within its maximum ratings, this guy here will work. It will saturate. It will turn on a light bulb up in Alaska in the middle of December. Of course, we're going into our spring, and the southern hemisphere is going into their fall, right? That's strange. So it's fall down in Australia. So IB, the saturated current, the minimum saturated current we need. Once you saturate the transistor, it's saturated. So it don't hurt to put more current into it. It hurts to put less, right? If I put less IB, then we're counting on a beta bigger than 30 to cause this thing to saturate. And we're not trying to create something that might saturate. We want to create something that's is going to saturate. Is going to be equal to what? 120 divided by 30, and what'd y'all get? 40 milliamps. 4 milliamps. Thank you. So we're using 4 milliamps to control 120 milliamps. So that means my little old switch over here only has to be rated at 4 milliamps, right? You understand? Very cheap. The lower the current rating of the little switch is, the cheaper it's going to be. So I have a little old tiny switch, right? You understand? Of course, we could latch this in too, but I'm not going to show you. We can use transistors to latch this in. Really, so I press the button one time and transistors would latch it in. I don't know if we'll have time to get into multi-vibrators. Okay, so let's look at what size resistor would RB be. And so this is going to be max. RB max. So that means even if it falls right on a standard resistor, we're going to do what with it? We're going to round it down. So it's just like the Zener. We're always going to do what? What's that? This here right here, by the way, I'm having a problem with. Yeah. So if y'all see me do this, I need to get me one of the big old bullhorns. Here and there. The ear doctor said it would take time. So what'd y'all get for, so here we're going to say 23.3 divided by 4 milliamps. So what would be the maximum size for RB? That's the maximum? Or is that what we choose? That's what we want calculated, and then we'll choose from there. You had to go all the way down to 2K?
I don't have this big stuff like things. I just whatever.
So what did we calculate?
Why we went
5.8. So what'd y'all calculate for RB? That's what, yeah, 5.8K. So we drop down here. So it looks like we might use a 5.6. So what would I do? I'd say 5.6 times 1.05. Y'all understand what the 1.05 is? That's increasing it by 5% for us, right? And what does that come up and give me? Okay, so we can't use that one. So I drop down to the next one. So we use a 5.1K right there. Yeah, there's no 5.4 standard.
on the map, they gave us use 5.1K
Yeah, that's the size resistor that we would use.
they gave us 5.4.
Yeah, 5.4. Okay. So this is the way we would do it. Now the problem is, and we'll talk about this next class. Well, we're going to be in laminate class. Is that this relay right here would blow that transistor up, and we'll talk about that why. We got to protect it. The relay is a coil, and when we energize the coil, of course we would have. Sorry, folks. When we energize the coil, it's going to drop 24 volts. Magnetic field is going to build up around that nice big coil. It's a DC coil, got hundreds and hundreds of turns of wire, because the only way it can get its resistance is by the gauge of the wire and the length of the wire. So you'll see these DC relays, they'll have tons of real thin wire. Okay. Then what happens is that that means it's time to let y'all go. What happens when we come up and turn the relay off, then what happens? Well, this magnetic field comes collapsing back into the relay. And when it comes collapsing back in the relay, the 24 volts don't mean anything, because what determines how much voltage that sucker induces back into that coil is the number of loops of wire, the strength of the field, and the speed of the motion. So that means we could get 100 volts off that coil if we didn't do something with it. 100 volts, a 3904 would probably break it over, and as soon as we broke it over, collector to emitter, what would happen? So we'll show you how to get rid of that counter EMF. We'll try to demonstrate it to you. So we'll do this while we're in lab. We'll get a coil and we'll hook up DC to it. We'll charge it up with 12 volts, and then we'll discharge that thing. About 70 volts, yeah. We did that in AC. We got to worry about that here, right? You understand that? So, and we'll show y'all how to get rid of it. It just takes a diode. It's not very much. See y'all Wednesday. What are we going to do Wednesday?
Yeah.
And who's not here? David and Wayne and David's not.